Hello, class. Okay, we're going to talk about an important application of magnetic fields. So we're going to start out, let's say we have a capacitor here. So there will be an electric field between the plates of the capacitor. Let's say we give the bottom plate a positive charge. The upper plate then has a negative charge. So the electric field would look like this. We have a constant electric field between the plates of the capacitor. And let's say we have a positively charged object and we send it through the capacitor. So we send it into this region with this upward electric field, and there's going to be an upward force on it. So it'll be deflected going through this region. And I'm going to draw a free body diagram of this particle here. We have an upward electric force, or let's say y direction. All right. Now, let's create a magnetic field in this region as well. So, let me just think for a second. We want this magnetic field to be out of the page. So we're going to use a right-hand rule here. So we have this positive particle, fingers in the direction of velocity, but we have to curl in the direction of the magnetic field, so that would be like this. And so thumb points downwards, the magnetic force would then be downwards. We're going to redraw this electric force. Red to match the electric field there. Just we don't get confused about which color is representing which type of field. Okay, so remember the electric force. And the magnitude of the electric force is just the charge times the electric field. And the direction of the electric force is in the direction of the electric field on a positive charge. Opposite for a negative, just like the magnetic force. The right-hand rule gives us a direction, in this case downwards. We would reverse that if we had a negative charge. And so both of these fields, the direction is given, for the particular type of charge. So if we reverse the charge, we're going to reverse both of these directions. So if we send a negative charge, we'll have an electric force downwards and a magnetic force upwards. And the point is they're going to be opposing each other. Now if we look at let's look at the net force in the y direction. The way we did this, that would be QE minus QVB. Now the formula, we have a QVB sine of theta. Theta is the angle between the velocity and the magnetic field. So we have a velocity in this direction, the magnetic field is coming out of the board. They're perpendicular to each other. That's a 90-degree angle. And sine of 90 is 1. We can factor the Q out of it. And that's the force in the y direction. Now imagine that we have this particle is moving very slowly. The electric force does not care how fast this particle is moving. The electric force is always just QE, where the magnetic force does depend on the velocity. So if we have very slow-moving particles, this magnetic force is going to be small, the electric force is going to be relatively strong, and the particles are going to be deflected upwards. And if we increase the velocity, let's say we make the velocity very high, then the magnetic force is going to be stronger, and the particles will be deflected downwards. And so there's one velocity if we get the velocity just right, it's going to pass through this region with no deflection at all. And that, of course, will occur when Fy equals 0. So no deflection occurs when Fy equals 0. Or if we just set this equal to 0, we have E equals Vb, or V is E over B. So the particles moving with this speed are going to pass through this device without being deflected. And you can imagine at the end of it, say you put this in a box, and you have this plate here, that if there's no fields at all, it'll just pass through. Now you put on the electric and magnetic fields, and if there's any deflection, if they've got a narrow opening to get through, any deflection, they're not going to make it. And so you can very carefully select the velocity that you want to get through. So imagine that these particles are, these are positive ions, for instance, in a gas. We know they move with a distribution of velocities. What if we just want to have a uniform beam of particles all moving with the same velocity? We run it through this device, which is called a velocity selector. So if you have a particular speed in mind, you just pick this ratio, E over B, to be that speed that you're interested in. And you can pick that ratio with a, you can pick one field and solve for the other, but just set that ratio to be the velocity you're interested in. Now there's actually this device has a lot of applications. I want to go over one just because it's interesting and also historically very important. This was a device, first J.J. Thompson. He was a scientist in the late 1800s and early 1900s. He had this device that looked like a tube. And then there's a photographic plate here. So if you have a charged particle hit this plate, that's going to light up that spot. This is how the old-fashioned TVs. If you ever see like a boxy TV, you might have one at home, obviously an old one because they don't use this anymore. But they use something called the cathode ray tube, where they have a beam of charged particles, and when they hit the plate, they cause it to light up. And that's how the first TVs were designed. You have this beam, you can kind of have it scroll across the screen, and it doesn't create like a uniform picture. But anyways, so the screen will light up if a charged particle hits it. Now, J.J. Thompson, I have no idea what his name is. Everyone calls him J.J. Thompson. But he won a Nobel Prize for discovering the electron. And one thing he'd do is, this experiment he did a little more than just discover the electron. But there's a filament here, which you can heat up, and they'll give off particles. So like, they're still debating the existence of atoms in the early 1900s. But they didn't really know what they were, and this was a major discovery, the discovery of the electron. So atoms generally are electrically neutral, but now we know that they're made out of positive and negative charges. So you heat up this filament, and we can cause these charged particles to go shooting off the shooting off the filament. And let's put a velocity selector here. And let's put the electric field just like before. Let's say we don't have a magnetic field right now. So we have a velocity selector here. We set up an electric field by just hooking the capacitor up to a battery to separate the charges. And we have this beam of particles, and you run them through this device, and you're going to get a beam that's going to look something like this. And so right away, you can actually see where they're hitting this plate. And right away you can tell that these are negatively charged particles. Because when they're in this region between the plates, they were deflected downwards. So if the electric field is upwards, force is downwards, that means that these are negatively charged particles. So I forgot one detail. Let's accelerate these particles through a potential difference v, like before they enter this velocity selector. And so, we've got this stream of particles, they're deflected downwards. That tells us these are negatively charged. And now let's apply a magnetic field. So what Thompson did is he applied this magnetic field so that, we still want it coming out of the board. Let's double check that. So this charge, the electric force now is downwards. And the magnetic force, again, right-hand rule, velocity, curl in the direction of the magnetic field, thumb points downwards. They're negative charges, so you flip it over. So again, with no magnetic field, these particles are deflected downwards. You can see where they hit the plate. And then we create this magnetic field here. And we're going to learn later how, just like we can use a capacitor to create a constant electric field in a region, there's a device called a solenoid that can create a constant magnetic field. And so we do that. And then we just keep increasing the magnetic field until this beam of electrons just flies through and hits the center of the plate here. And in this case, we know that the magnetic and the electric forces canceled out. And so from our velocity selector part, let's do this. We've got two things we want to consider. Let's do it one thing at a time. Let's say we start at point A and end at point B, and say these particles have essentially no velocity at point A. So they have purely kinetic energy, QV. Or because we know we're talking about electrons, but Thompson didn't know that yet, but there was just some new particle they discovered. But we know the charge E, and this is the potential energy at A, and that's equal to the kinetic energy at B. So again, we have to be a little careful here. This is a capital V for potential. This is a lowercase v for velocity. And so the particles accelerate in this region with a potential difference, and then they enter the velocity selector. And from here, we can say that E is V over B. So again, that's a velocity. So I'll write VB. Let's solve for a velocity. I think I got that last equation mixed up, so let's check. We have QE minus QVB equals 0. So VE is E over B. Okay. And so let's put these together. Let's multiply by 2. So we have, I got rid of the 2, so 2EV is mVB squared, where again we know that the velocity of these particles that are passing through undeflected is E over B, and these are variables that we selected, we picked. So we can control the electric and magnetic field. Remember, he fixed the electric field in between the plates of the capacitor and varied the magnetic field until this happened. And so what Thompson discovered we write it down. So E over M so yeah, let's solve for this ratio E over M. So we have E squared over 2VB squared. And everything on the right, these are variables that are controlled by the experiment. Like you pick E, you pick the potential difference that you're accelerating these charges through, and then you vary B until you get the condition you want, that they pass through undeflected. And again, let's assume we do this in a vacuum. And so we can determine the charge to mass ratio of the electron. And Coulomb did this over 100 years ago, right when they discovered electrons, and his value was very, very close to, like the currently accepted value using kind of more precise techniques. But yeah, very important experiment historically. And again, just discovering this new particle, but this gives us an idea of the size of the particle. Very, very small. I mean, they didn't know the mass or the charge of each yet, but this was a vital step in kind of putting together this picture of how atoms work. So, very important discovery. Okay, so again, that's just one application of a velocity selector. But you can imagine many others. Anytime you want a beam of particles, make sure they're moving at a particular velocity. Here you go. Okay, so that'll be it for now.